Welcome. In this video I would like to demonstrate how the activation energy can be determined from conversion data. This video is focused on the usage of the Akahira Sunose method, KAS method for short. The conversion data here will be generated by employing the pyrolysis modeling capabilities from FireSciPy. In a later video I will discuss how to use data from thermogravimetric experiments instead of data from the model. In a previous video I gave an introduction on the modeling capabilities of FireSciPy. There it was also discussed how to install FireSciPy, where to download this notebook that I'm showing you here, as well as where to find the documentation. Please note that the imports of various packages also have been covered in this previous video. This section here starts out with some brief theoretical background. The focus is here on a single-step pyrolysis reaction. The conversion rate, d alpha over dt, can be expressed as a rate constant, the k depending on the temperature, as well as a reaction model, f of alpha. Typically, this rate constant is expressed by an Arrhenius equation. This has two parameters, the capital A as the pre-exponential factor, as well as a capital E, which is the activation energy, the thing that we are interested in. With that, we can rearrange the above equation. The reaction rate then only depends on the pre-exponential factor, the activation energy, as well as the reaction model. These three together are what is called the kinetic triplet. If we now want to deduce the activation energy, we can take the logarithmic derivative of the above equation. For a fixed level of conversion, meaning for a fixed alpha, we can then neglect the reaction model f of alpha. This is the reason why these methods are sometimes called model-free. Within this computation, it is at some point necessary to compute some temperature integral. However, this particular integral has no analytic solution. For that reason, it is approximated. Now, there exist many model-free methods. The difference between those is how well this particular temperature integral is approximated. A fairly well-known method is the Ozawa-Flynn-Wall method. The method that I'm using here, however, is the Akahira Sunose method. This offers a higher accuracy in the approximation of the temperature integral. And it is not only just the Akahira Sunose method that I'm using, it is also further including the Starink improvement. For further information, please check out the links that are provided at the end of this section. More details of the theory are covered in a different video. Here the focus is on the usage of FireSciPy. At first, the reaction rate is defined. This will later be used for the synthetic TGA data generation. FireSciPy also introduces a data structure. This is used to store the data that is related to the kinetics computations. This data structure is initialized as an investigation skeleton. It allows you to provide some metadata for your investigation. For example, what material are you investigating, or at which date did you run the experiments. It further requires some information about the signal. For example, in this case, I'm assuming to have used TGA data. Therefore, the signal that I'm interested in would be the mass of the sample. We can also provide a unit, in this case it's milligrams. This data structure is not only used to store the initial data. It will also contain the intermediate results that have been generated during the computations. As the next step, the temperature programs are defined to create the synthetic data. Keep in mind that the ICTAC recommends to cover a factor of 10 between the lowest and the highest heating rate. Moreover, one should use at the very least 3, better are 5 or more heating rates to perform the kinetics computations. Later I will briefly talk about what these recommendations aim to achieve. For this example I've chosen to use 7 heating rates. The temperature resolution should also be high. Here it is set to 0.5 Kelvin. Feel free to download this notebook and play with the parameter to see its effect. Temperatures are required to be provided to FireSciPy in Kelvin. The temperature time series of the linear heating rate programs are generated like discussed in the previous video. They are then used to compute the conversion. Different than before, a data frame is created and manually stored inside the data structure. This is only necessary because I have used data as input that was generated by a model. When you are using experimental data, the pre-processing steps will automatically lead to the same state of the data structure. If you watch the next video, this will make much more sense. Now I'm just trying to make sure that the next processing steps work properly. In the following step, a set of desired conversion levels needs to be defined. They are used to interpolate the data from the temperature programs to the same conversion points. Typically, they range from 5% to 95%, sometimes also from 10% to 90%. This depends a bit on the data quality. The spacing is 1%. Here, the input is model data with very little noise. Based on this, I have chosen a range between 1 and 99%. In the next video, I will show an example with experimental data. Then you will see why pieces are cut off in the beginning and the end. Afterwards, the conversion is computed. The data structure needs to be provided as well as the desired conversion levels. The setup distinguishes between experiments conducted with constant heating rate or isothermal. This information would be provided when the experimental data is stored in the data structure. The condition describes how the experiment was conducted. Here I have chosen constant heating rates. All the experimental data is stored, sorted by these conditions. The conversion can be computed for individual datasets or, like here, for all that are available. The function knows from the data structure where to find the input and where to store the output. Now let's compute the apparent activation energy using the Kissinger-Akahira Sunose method. By default, FireSciPy uses parameter values for B and C from the starring improvement. Again, the data structure needs to be provided to obtain the input data from the previous step and also store the output. Alright, let's have a look at the results. This plot here shows the activation energy over the conversion. The black dashed line represents the value used to generate the synthetic data. It is here used as a target to assess how well the computation performed. The blue circles show the values of the activation energy per level of conversion. They are basically forming a horizontal straight line. Thus, the conclusion can be drawn that there is a single-step reaction with an activation energy of roughly 125 kilojoules per mole. The gray areas at the beginning and the end of the plot highlight the initial and final 5% of the conversion. Remember, I mentioned earlier that a common range to assess the activation energy lies between 5 and 95%. This is primarily driven by the quality of the data, but also, or maybe even more important, the limitations of the experiments. This will become clearer when we are talking about how to process the experimental data in the next video. Regardless, I personally would suggest for you to compute the data over the full range and then highlight the areas that you would like to cut off, similar as it is done here. This will provide more transparency to the readers of your work. Now let's talk about some of the data recorded during the kinetics computation. FireSciPy keeps track of the intermediate results. For example, the desired conversion levels are plotted here against the sample temperature. By definition, the conversion is 0 if the reaction has not started yet. For example, look at the blue dots at the bottom left. The conversion is 1 once the reaction concluded. Again for the blue dots here at the top. Somewhere in between is a transition where the reaction is actually happening, visualized here from the S shape of the blue dots. With higher heating rates, the reaction shifts to higher temperatures. This is also nicely visible here. This phenomenon is used to determine the activation energy and forms the basis of thermal analysis. Another example are the results of the KAS computation. These are stored inside a pandas data frame. The first column contains the conversion levels that we have defined above. In the second column, the values of the respective activation energies are stored. It holds information for the linear fit per conversion level, statistics computed for the fit, as well as the coordinates of the points used for each fit. These individual points and their respective fit are visualized in the following plot. The colors match the data series in the plot that I showed above. Remember the equation from the beginning. We can use the left-hand side as y and 1 over t as x. Then the activation energy can be determined from the inclination of the linear fit. And here is where the recommendations come into play that I've mentioned earlier. The factor of 10 pushes the data from the lowest and the highest heating rates further apart in this plot. Compare, for example, the line of the pink circles for the 60 Kelvin per minute at the top with the line of the orange circles for 3 Kelvin per minute or the blue circles for 1 Kelvin per minute at the bottom. Using multiple temperature programs distributes more data points along these dotted lines. These two aspects lead to a higher accuracy of the linear fit. And again, the inclination of this fit is what gives us the activation energy for a specified level of conversion. And as I already mentioned, for each of these fits, some limited statistics are computed here as well. These are shown here in the next plot. In case of the model data that I've used, the R squared is basically 1 and the root mean square error essentially 0. This indicates a good fit throughout the data set. This also allows us to use the full range of data, meaning from 1% to 99%. We do not need to cut off the ends that are indicated here as the gray boxes for the leading and trailing 5%. So we have reached the end of this video. The next one will talk about how to process experiment data. Thank you very much for your time and have a nice day.